Okay, so we're talking about the relationship between heat and temperature, and this is going to be talking about the Carnot corollary. Now, the Carnot corollary, named after a Frenchman named Sadi Carnot. And Sadi Carnot was thinking about these ideas really early in his life. Sadi Carnot in the 1820s, he was 27 years old, and he was thinking about all these ideas about how thermodynamics works and about the second law of thermodynamics well before it was ever really thought about. He was well before his time. But here's the problem. There was a pandemic that went out. Cholera was going around, and he died. And he submitted some papers to get published, and they got out there to be published. But all his other work, when you had cholera at that time, you were burnt, and all your surroundings were burnt because they didn't want to pass that disease off to other people. So Sadi Carnot died, and all his books and all his research was burned with him, and he might have propelled us way far ahead in the idea of thermodynamics. And it wasn't until after his death that his papers that he submitted before his death gained some notoriety, and people started saying, hey, this guy was on to something. And so we started naming things after Carnot, and you'll see a lot of things come with Carnot's name to it because it's some very interesting research. Again, he was 27 years old when he came up with all this. All right, so the Carnot corollary says this: all reversible heat engines have the same efficiency when operating between the same two thermal reservoirs. No matter the working fluid. Okay. The Carnot corollary says if it's reversible, if it's the best it possibly can be, then it's got to be the same if you're attaching it to the same hot and cold reservoir. So here we go. We have this hot reservoir, and we have this cold reservoir, and we have these two cycles, 1 and 2. We're saying that the efficiency of 1 is equal to the efficiency of 2 if both are reversible. Okay, that makes some sense. If it's the best it possibly can be, then it doesn't matter if it's running water, ammonia, R134A, air. It doesn't matter what's inside of them. They're going to both give you the same thing. Okay, ideal is ideal. Okay, reversible and ideal are sometimes interchangeable words, as in irreversible and real are real words. So the question was, can we relate efficiency to the temperature of the reservoirs? Okay, so what we're going to do here is we're going to say, can we say that QC over QH for reversible systems can it be some function? This is saying some function, this is a psi, some function of the temperature of the reservoirs. So this means some function. Okay, now there is a proof on this. I mean, you might say I do a lot of proofs in class, and I do some proofs in class, but this is a really serious proof. This is a conceptual proof that jumps through a lot of hoops here. And it was created by a man that we now call Lord Kelvin. And his proof to this said, why don't we make a simple choice? So Lord Kelvin here made a simple choice. He said, why don't we make this function, why don't we just make that equal to a Tc over Th? Okay. So if I do that, then I can say that Qc over Qh for reversible systems is equal to Tc over Th. And they said, how are you going to do that, Lord Kelvin? He said, well, I'll create my own temperature scale. And that's exactly what he did. He created an absolute scale. That satisfied this. And he liked the Celsius. He thought the Celsius scale was a very good one. You have from 0 degrees of freezing and 100 degrees of boiling, had 100 even steps. He really liked that, so he kind of latched on with that step size and said, what we'll do is, if you look at this, we can say QC over QH times TH is equal to TC. At absolute 0, when you're at 0 degrees, you're going to have no heat transfer. And so if you have QH, you have no heat transfer, 0, you're just going to have a temperature of 0. And then every time that we would add a little bit of heat, then we could have some temperature, okay? And that's what he created. He created a temperature scale to work with this. And that's been a blessing to thermodynamics, and that's how we use it to calibrate the triple point of water. We calibrate water, the temperature scale, let me say that again. We calibrate this scale at the triple point of water, and that's where solid, liquid, and gas all appear together, the triple point. And so it's important that we know that's kind of how the Kelvin scale came up, and that's how our scales are all calibrated now at the triple point of water. But we have to remember this is created for reversible cycles, okay? Reversible cycles. So for reversible, we know that QC over QH reversible is equal to TC over TH. We know that QH over QC reversible is equal to TH over TC. It's the same thing. Or we could write here that QH all over TH is equal to QC over TC. And we have to remember this is reversible. Okay, so what does that do for us? Well, that does something very valuable with our efficiencies. So let's go back and talk about our efficiencies and our coefficient of performance. Okay, so our actual efficiency that we can calculate is always 1 minus QC over QH. But you can see that this can be for a real cycle. But what happens if it's for an ideal or reversible cycle? We can rewrite this as in maximum is equal to 1 minus Tc over Th. This is what would happen. This maximum would happen if we have a reversible cycle that we're dealing with. Okay, we can do Tc over Th here. And we can do a similar substitution for all our coefficient of performances. And it's not as, if you want to look at how we actually go from QC over QH to TC over TH, it's pretty easy. But if we look for like beta actual is equal to 1 minus, sorry, not 1 minus, it's equal to QC all over QH minus QC, and beta maximum, beta max is equal to TC over TH minus TC. It looks like we just replaced the temperatures. If you have a TC, it's a QC. If you have a QH, it's a TH kind of thing. And you also have gamma actual, which is equal to QH all over QH minus QC. And gamma maximum is going to equal to TH all over TH minus TC. Now these things over here, these are called the Carnot. So they're either called the Carnot efficiencies or the Carnot coefficient of performances because they come from that idea that Carnot created. And so now we can look at two reservoirs, a hot reservoir and a cold reservoir, and we can say, okay, here's the maximum efficiency that we can get out of this reservoir if we use, and it's important that it comes from because these TC and TH must be in absolute units. They have to be because that's what was created to make this substitution work. So you must remember to use absolute units here. But we can look at these temperatures of reservoirs and we can say, okay, if we're running between these two reservoirs, this is the maximum efficiency that we could get. And if we set maximum equal to actual, saying let's say our actual got up to the maximum, we could find out what heat transfers we would get to meet that maximum condition. Okay, if we set in max equal to in actual, we can find that out. Same thing goes with coefficient of performances with refrigeration and heat pumps. So all real processes, here we say, all real processes must be greater than or less than or equal to the max. Okay. All real processes, all real cycles, I should say here, must be less than or equal to the max. So we can check to see if cycles are real by checking their actual efficiency to their maximum efficiency. If we're less than or equal to the maximum, we know it can be a real cycle. Now, you may make the argument, well, Dr. Wanklin, it's a cycle. We can't be equal to the max. I agree with you. But what we're going to say here is that it has to be less than or equal to. We're going to have the limiting condition that is we can reach the maximum efficiency. Okay, so these are some very important ideas that we're going to end today by doing some problems where we're going to analyze these. And so all that stuff that we talked about back in chapter 2 about cycles, about finding the efficiencies, now we're going to revisit and do it all again. Every problem I've asked you about, I can ask you the same problem again and ask you about the maximum efficiencies. Okay, so be careful and be ready to experience that good stuff. Okay, we will do those problems after the break.